Okay, good morning, good evening, good afternoon, everybody. Welcome to the second day of the mentorship week. I'm extremely excited to welcome Roberta Sinatra to the summer school. I am very, as you probably been witness to my hyping of her talk, of her research in general. I'm very, very looking forward to her talk. So Roberta is currently an associate professor in data science and network science at ETU Copenhagen and holds visiting positions at EC Turin, Italy, Complexity and Science Hub, Vienna, Austria. And starting in October 2022, so recently, she will be a professor in social science. I'm sorry, at the social data science at the University of Copenhagen. She is the coordinator of the Networks, Data and Society Nerds Research Group and co-lead at the AI Pioneer Center in Copenhagen. Her research is at the forefront of network science, data science, and computational social science. Currently, she spends particular attention on the analysis and modeling of dynamics that lead to the collective phenomenon of success, with a focus on science and art and on data for good applications. Her research has been featured everywhere, including the New York Times, Forbes, The Economist, and The Guardian, and The Washington Post, among other major media outlets. Her research has been awarded the Complexity System Society Junior Prize, the DPG Young Scientist Award for Social and Econophysics Science, and a Billum Young Investigator Grant. So with that, please join me in welcoming Roberta. Roberta, looking forward to your talk.
Thank you. Thank you for the very detailed introduction. And I'm excited to be a mentor, to speak at the Science of Science summer school. This is really a topic very close to my heart. So let me see if after 2 years of pandemic, I'm able to share the screen without incidents. Yes.
Perfect.
Perfect. I just want to have the chat box. Okay, I have it here. Perfect. All right. And I don't have the participants box in front of me, so don't use the raise hand functionality, but just type something in the chat or speak. I don't mind. So questions are welcome throughout the talks, not just at the end. All right, so thank you for the introduction, and I learned that this topic or this talk was awaited, and I hope to raise to the occasion and to the expectations. So I want to talk about biases that we experience and that we can measure in a scientific enterprise. And I want to start with, sorry, it's not changing slides, so my pointer is somewhere else. Okay, here. And I want to start talking about an effect that we experience in many social systems, including science. And this is the widely known phenomenon called Mafia effect that says that the rich get richer. It's a phenomenon that, depending on the field, has different names. So, for example, in network science, people tend to talk about preferential attachment. If you are from the information sciences or from social science, we talk about cumulative advantage. Mathematicians talk about Poyer-Earn, but it's basically at heart the same phenomenon. It has many names because it's found in many systems, and it drives the evolution of popularity and impact. So, for example, it describes how papers tend to acquire citations over time, or in a platform like Twitter, it says how tweets are retweeted or how we watch videos. Crucially, and this is a very important point, it has a very clear mathematical formulation. So, for example, if we talk about citations, the Mafia effect says that the probability of acquiring a new citation depends on how many citations you already have. So this is what the formula on screen says. And this probability can be tuned with some constant parameters. We can, if you want, in the Q&A, we can discuss more about this, or in the mentorship shaped sessions. But this is what really captures that the probability of acquiring new citations depends on the citations that the paper already has. Now, there is also another phenomenon which has been documented in many social systems, and it is called the Matilda Effect, and basically says that there is a bias against acknowledging the performance of women. And this is also an effect that drives popularity and impact. Now, here I'm talking about the Matilda effect, but in general, and despite a key point is that despite being well documented, this effect has surprisingly no real mathematical formulation. There is no formulation that describes the evolution and the effect of the Matilda effect over time. So the Matilda effect describes essentially a gender bias that we witness in academia and in science, but similar biases have an effect also, exists also towards ethnicities or affiliations. So for example, we can name this effect as the X effect, which basically says that the bias against acknowledging the performance of X exists. So I'm just want to say this because there are many biases, not just the gender biases, and we can use under certain conditions the same framework, the same analytical statistical framework to analyze these different biases. Why is this important? Why have I started talking about the Mafia effect and the Matilda effect? Well, because these two effects indicate that the social measures like citations that are widely used in science and in quantifying science evolve in a biased and strongly coupled way. So bias, the Matilda effect says that a bias can exist and can create a small difference in, for example, citation trajectories, and then the Mafia effect can amplify these differences. At the same time, we are increasingly using algorithms that are trained on social measures, that are trained also measures based on citations. And we treat this output of algorithms as proxies of quality and of performance. So what happens is that algorithms can become inherently biased too and can amplify inequalities. Also in science, also on algorithms, also in systems that use those data sets that are widely adopted in the science of science. Let me give you a practical example of where this can happen. And so the core of paper ranking algorithms could be Google Scholar or any paper ranking algorithm that you can think of. It's usually a black box which takes information about paper, like title, affiliation, and crucially citations. And these algorithms typically tend to rank papers with many citations higher than less cited papers. It's not systematically, but statistically speaking, they do this. And this usually sounds right, sounds legitimate. Yet these algorithms are biased because there is experimental evidence, scientific evidence, for example, that given same quality, given the same paper, women or population, different segments of populations tend to have different recognitions. So the papers of men tend to be ranked higher than the papers of women, and this can result in different differences in visibilities between men and women, and also different recognitions that are based on this visibility or on indicators that that are inherently biased too because of the original bias that we find in the data. So, the citation bias can have many consequences in the output of the algorithm that we use, on indicators that we use. So what is my motivation lately? One of my, I would call it almost obsession, is to understand and model quantitatively the bias mechanisms that, given the same object, given, I call it the same quality, same performance, create a divergence in citation trajectories, for example, based on different attributes. It could be gender, it could be affiliation, it could be ethnicity. And then I would like to use this bias mechanisms knowledge to open the black box, to understand what happens once we put this knowledge, what happens in the to the output of the algorithms. Is that output biased? Can we correct for that bias? Can we create basically an unbiased ranking or a fairer system? This is a bit the motivation, and where is it going? I'm not here to claim that the problem is solved, but I want to show some steps and some of the research that I'm doing in this direction with this motivation, and yeah, to understand the bias mechanism with the overarching goal of creating a fairer system, or to decide that this system cannot work, it will always bias, but at least we are aware of it in a quantitative fashion. All right, so I've been working on quantifying that science for some time, and back in 2016, I was working on the problem of how does impact in scientific careers evolve. So I had no focus whatsoever on bias, but I was interested in understanding understanding and in coming up with models that could describe the career evolution in terms of impact for scientists over, say, 20, 30 years. And when I'm talking about, when I talk about careers, I have in mind something like this, where so this is the career, for example, of a physicist, Richard Feynman, and here each dot that you see on screen is one of the papers of Feynman, and the height of the dot is a measure, captures a measure of the impact of that paper. Here is citations accumulated over 10 years. You can choose different measures of impact. And we were interested in understanding the ups and downs of these careers, not just the one of Feynman, but of all the scientists that we had in our data. And we specifically wanted to understand whether our models could predict the highest impact paper of a scientist, and when this highest impact paper occurs, and what is the magnitude of that paper, the magnitude in terms of impact of that paper. Now, I will not cover this research. What I need here for the purpose of this talk is that you know that we introduced a model called the Q model. This is a model that basically associates one scientist with a number, with a parameter called Q. And this Q manages to reproduce the ups and downs of a scientific, of these plots that I showed you. So there are ups and downs of a career. And this works for 85% of the scientists in our data set. So we had, basically, we're interested in having a model that gave us one number which could capture the statistical properties. And if you're interested in knowing more about this paper, the paper is published, or there are also online resources like a video on YouTube and a platform to explore interactively the data. But yeah, so from this research, we knew that these careers could be summarized with one number. And then this is where a bit my obsession, my interest in biases started. So there was a lot of this paper received a lot of coverage, and many people, scientists, funders, and so on, started equating Q, this parameter that I was talking about, with quality, performance, a way of ranking scientists, and so on. And this is a bit sometimes what happens with our research, that it gets unintended consequences, or consequences you couldn't anticipate. We were interested simply in models to reproduce the ups and downs of careers, and this is instead where it ended up. And this is when I started reflecting on these questions, whether the measures, any measure of impact that we can come up with, so impact here is captured by citations and derivatives of citations, can really say something about performance in science, something which is even vaguely related to quality. So this is my key question: how do performance and impact in science differ? And if we can understand the difference, whether we can quantify the differences between these two concepts. And I started focusing on one variable that is associated with a difference between performance and impact, and it's the gender variable, but there are many more, as I mentioned earlier, and I will mention some of them later. So if we take this parameter Q, and we measure Q in the population of female scientists and the population of male scientists, we see that there is a systematic, there is a difference. So the male scientists have a Q, this parameter, which is 15% higher than women. But this doesn't tell us much, right? It could be that there is a statistical bias because of the way statistics are created, or if we believe that Q really captures performance quality, it could support the hypothesis that male scientists typically produce work which is better, with quotes, right? Better than work by female scientists. So this is a chicken and egg problem, a problem which is really hard to, a question is hard to answer, unless we can have controlled experiments where, for example, we could keep quality constant and just change the gender of an author. Now, this is basically impossible to do with in our setting where a paper is published and there is a definite author for that paper. But we had in mind the setting of controlled, randomized control experiments, which we wanted to transfer, to export to data, to understand whether gender has a role in differences in impact. So the questions that we wanted to tackle is, what is the role of gender in career differences, with everything equal in the system? And in particular, how does productivity differ between female and male scientists, and how does impact differ between female and male scientists? And the reason is that productivity and impact, and many measures based on productivity and impact, are usually used to evaluate in different ways the output of a scientist. So the first thing that we did was taking the careers as the ones that I showed you earlier, and label the gender of these careers based on the first name. And here we use binary gender, which is of course an approximation, but this is what the data allows us to do. So, and so in our framework, we just have female scientists and male scientists use exclusively based on their first name. And once we separate careers into female and male careers, one could do usual measures straight away, like measures of productivity, how many papers a scientist produces, or impact, what is the average number of citations a scientist gets, and so forth and so on. If one does this kind of measures, we find differences basically everywhere, differences between males, between men and women. And I just summarize some of these differences for you here. So in our data, men constitute 70% of the scientific workforce. They get 30% more citations. They are more productive, and the gap in productivity seems to increase. It was 10%, men were 10% more productive in the 50s, and in the 2000s, they were 35% more productive. However, in this data, women and men have the same annual productivity. So on average, a man and a woman have the same, publish every year the same number of papers, which means, to be consistent with the other data, with the higher productivity of men, that women tend to have shorter career lengths. So they publish at the same rate as long as they stay in science. And actually, this dropout rate, so the shorter career length of women, means that women tend to drop out at a higher rate than men from academia. And this dropout rate is not constant throughout a career, but it's actually very similar between men and women at the very beginning, in the first 3-4 years. So usually when scientists are doing their PhD. And then it starts diverging, starts opening, so that then women tend to drop out at a higher rate than men after these first few years. And the highest gap in dropout rate is actually 7 years into scientist career. So this is usually at the time of a postdoc or when entering the tenure track system. So, but all these results that I talked about, these differences, can be a result of many confounding factors. So we really cannot have a good, so there are these differences, but their causes are unclear, right? We don't know what causes what, whether, for example, men tend to have more citations simply because they are more productive, or whether men are more productive because they are in better ranked universities, institutions that provide more resources. So there are plenty of confounding factors. And here is where we tried to use a system which is similar to the one of randomized controlled experiments. So we were working with huge data sets that had basically millions of careers. And thanks to the volume of data, we could use an approach called matched sample approach, which is something which gets as close as possible to controlled experiments, but in observational data. And this matched sample approach basically constructs two samples, one of female authors and one of male authors, where we try to match all possible characteristics so that are measurable in the data. This is something important to stress. So for example, for each American physicist with a career of 10 years that works at an institute ranked in a certain way, that is female, we found someone identical in the male population, which is also an American, physicist that has also a career of 10 years, that is also an institution ranked at the same level, and so forth and so on. So we matched variables and we create two matched samples. The differences between these two samples are the gender and the variables that we do not match. In our case, we do not match first for productivity, and then we do not match for impact. And all other measurable variables are matched. So if we create this matched sample approach and measure, for example, total productivity. So first we measure total productivity, so how many papers a woman and a man produce in the population without matching, straight away in the data. And we find, as I mentioned, 27% difference between men and women. Then we create a matched sample, so all these variables are equal between men and women, so topic, nationality, and so on. And then this productivity gap in the matched samples shrinks. It becomes 7%. Same thing can be done with impact. If we measure it straight in the population, there is a difference of around 30%. If we measure impact after controlling for all the variables, including productivity, then basically there are no significant differences between men and women. So this basically tells us that the differences in career length and the different distributions of population of females and males in disciplines, in institutions and so on, can explain many of the differences in productivity and in impact. So if we go to our questions, how does productivity differ between female and male scientists? Well, only by 8% if we take into account discipline and the dropout rate. And how does impact differ between female and male scientists? There are almost no difference if we take into account confounding factors. Now, take these results with a grain of salt, because the specific conclusion, the specific interpretation that I'm presenting to you can be, I mean, we have a conclusion, but this conclusion can be different if you use a similar approach in different data sets. So, for example, I know that Ludo's listening, but there are different other analyses based on that study gender bias on different data sets with different timeframes and so on, that tend to reach different conclusions about what we need to match to find no differences in productivity and in impact. But I think what is important here, this setting, is that no matter what, when we don't match, so when we do an analysis of publications, citations, grant funding, and so on, we do find always differences between men and women. So without the sophisticated statistical approaches, there is a difference. Now, these differences are then are present in the data, and this data is fed to algorithms, is fed to measure. Then those measures, those algorithms, those indicators, they do pick these differences. And we need to know that these differences are present also down the line in what we do, and we need to understand the impact of those differences. So what we are working on these days with colleagues and people in the NERDS group is to understand how the gender disparities affect algorithms, like ranking algorithms. So if we take a data set of citations, that uses the citation network, it could be data from the now defunct Microsoft Academic Graph, but it's well, if you take just citation network data, where you can label the gender of the nodes. You can then construct a rank which takes into account all the information that is embedded in the network. So the page rank is a network measures that ranks all the nodes, taking into account all the relations between all the citation patterns that are present in the network among the nodes. It's a ranking that is at the core of many ranking algorithms, like Google Scholar or other information retrieval systems. And we wanted to understand how the gender bias that we find in the data can affect page rank. So we wanted to ask, how fair are these rankings based on citation networks, and how can we increase the fairness of this ranking? With the idea that when I rank information, I usually tend to look only at the beginning of the ranking, and that if we assume that men and women or different segments of the population produce works that should have the same visibility because they are supposedly of the same quality, then we want to have rankings that are as fair as possible in terms of representing the population at the top of the ranking. So considering all the gender gaps information that we have in the data, we expect that rankings could be highly unfair in terms of visibility. So let's see what I mean. So first, we need to understand. We need to have a measure of fairness. Is this ranking that I show on the screen fair? And one common measure used in algorithmic fairness is it's called demographic parity, that basically says that if I have a population, here in the example for simplicity is 50% men or 50% and 50% women, the fairest ranking that I can have is a ranking where at any point it shows 50% men and 50% women in the top position. So if I take the top 1% of the ranking, I see 50% and men and 50% women. If I take the top 10%, again, I see 50%, 50%. This is the fairest ranking that I can get. It's usually not like this. If, for example, I take these two rankings, the one on the left and the one on the right, I see that the ranking on the left has a statistical parity at the 6th position. So if I scroll 6th position, I find 3 men and 3 women, 50%, 50%. While if I go on the right, the statistical parity or demographic parity says it's the same, is achieved only at the 8th position. So if I stop at the 6th position, I find 2 women and 4 men. So this is not, there is no parity here. So the ranking on the left is fairer than the ranking on the right when I look at the top positions. Okay, there is a question on the chat, I guess about matching variables, and I'll tackle this. It's on the back of my mind. I'll tackle this as soon as I finish talking about rankings, so it's not overlooked. So we started studying the ranking of citation networks of different disciplines, economics, chemistry, psychology, and mathematics. And just as a side note, these are huge networks with millions of nodes, and it can reach billions of links. So it's also a computational, non-trivial computational effort to calculate the page rank. In this case, there was a very talented student at ITU that managed to tame the size of the network, so we could manage the page, we could calculate the page rank in these disciplines. And we wanted to understand where in the ranking we get demographic parity. So here you see 2 curves, purple one and light blue one. And in this field, this is economics, we don't have 50% women and 50% men. We have roughly 75% men and 25% women. And we look when these 2 curves reach parity, when we find basically the same number of men and the same number of women at which threshold of the ranking. And in this case, we had to scroll down down to 81% to find the same number of women and men. So demographic parity is reached at 81%, which is quite of uneven or unfair based on fairness measures, unfair results for this ranking. And economic is actually one of the worst in terms of fairness in the ranking. Psychology is one of the best. It reaches statistical parity at 63%. And it's one of the best, so it's still, so we see that these rankings tend to be very unfair in terms of visibility of women versus visibility of men. And this is done on unmatched data. Now that we've talked about matching, you know, that we can construct better balanced data sets and study the fairness in balanced data set where we are aiming for some of the confounding factors. And if we do the same ranking in balanced data set, we see that the rankings are fairer. So in the case of economics, we reach statistical parity at 30% as opposed to 80%. Which means that we can use the framework of matched samples, for example, in rankings, whenever we have to do a ranking, right? So we can filter some of the information to produce a fairer ranking. So it's a practical way to unbias or reduce the bias of algorithms. So going back to our questions, how fair are the rankings based on citation networks? Well, these are extremely unfair based on the notion of demographic parity. There are other fairness measures that one could use. We explored this one. And can we increase the fairness of these rankings? Yes, we can do by matching affiliation and career variables. So there are practical ways to reduce this. And I'm about to conclude. I just want to finish with two thoughts. So why should we care about correcting biases? After all, I mean, many people say this is how we work. This is how we humans work. We have bias that are reflected in how we cite work, for example, or how we produce data. But this is just an aspect of humans, as aspect of life. Well, I think that we should study bias, and here in this case specifically, we want to for example, improve the algorithms that are the core of our engines, like Google Scholar, Microsoft Academic Graph, or Web of Science, because we need science to tackle the challenge of today's world, for example, climate change. And we want to discover just the best and most relevant science that we have available, and not the science that is produced by a certain segment of the population. It could be the weird population, weird as in Western educated. Well, education is important here, but science that is produced by a very specific group of people. We want just to make sure that we get all the relevant and important information. And algorithms, we're not sure that algorithms are doing that. Algorithms are as good as the data that we put in, and we're putting in strongly biased data, biased based on things that have nothing to do with quality, with how we perceive quality. And the other point that I wanted to make is that if we have bias in the data, and we use this bias to do predictions, then we are perpetuating bias. We are perpetuating our opinions. And this is a point that we were making together with Aaron and Dan, that I know have spoken or will speak at the school at some point. So where we said that if we use biased data, for example, to desk reject papers, the algorithms that do this choice perhaps are not quantifying quality, but they are just picking on the fact that women or people from a certain segment of the population have lower chances of reaching the peer review system. So they are more likely to be desk rejected by an algorithm that should assist editors. So again, it's a very dangerous ground where we take biased data, we feed it to algorithms, and we make decisions based on that. So we should study bias to understand how this works. There are many more biases that I didn't explore here. Gender, reputation, interdisciplinarity, group size. These are just some of the biases that I've been working on in my research. So in the mentor sessions or whenever we can have a chat about this. And there are many more that the entire community is exploring. So do performance and impact in science differ? They do a lot. And I think one of the big challenges of the science of science is to understand why do performance and impact in science differ? So what are really the causal links in this? Because once we know the causes, we can perhaps have sound policy decisions, and how this difference affects our lives. Yeah, it's also something important to understand unintended consequences down the line. And this is also research that I'm doing, funded here in Denmark by two great funders. We'll skip this. I want to say that it takes a village to do great research and to do research in general, and also to do research one is proud of. And I'm proud of my many collaborators, not just on the project that I presented, but on the whole science of science line that I pursue. There are too many to mention, but they are all on screen. And yeah, and I want to thank you for your time and attention.
Thank you so much, Roberta. Great presentation. So I'm gonna open the floor for questions. There are two questions in the chat.
Yeah.
So if you want to unmute yourself, please, and ask the question, that will be best.
Sorry, thanks for your presentation. I would like to ask, a couple of questions, if you do not mind. My first question is that, when I'm living in a country, that capital city is very, very important. It means that there are a lot of job opportunities there, and people in any gender, they are, looking for that. And, when we are looking at the capital, you can see in my country, Tehran capital, it is, you can see that maybe 40% of clients are women, or maybe 60% are around men. So I would like to say that when we just go to small provinces, that the job opportunities are very small, those opportunities are going to be assigned to men, because they are going to just have families, and they are going to pay for that. So I would like to say, when you're going to just pair two persons that they are really similar to each other, about when they are how they are working, and also maybe their age, or anything that you just looked on, it is really important to say that where do they live. Means that think about the situation that they are living in Bay Area. Maybe a girl or boy in Bay Area, they both have same opportunities, but maybe when we go to small states, or maybe small cities, it is completely different. So I would like to say that maybe there is a bias in your research too, that you're not looking at the location too. Yeah.
So let me answer this to this comment. Is more a comment than a question in two ways. So first, so specifically about the research, I mean, we match for affiliation that the scientist has. So this supposedly correlates where you live. So if you have the affiliation, I see the question about the Bay Area, right? If you have an affiliation which is Stanford University, supposedly you live in the Bay Area. So we implicitly match on where you live. Of course, we cannot match on where you live in terms of neighborhood or socioeconomic conditions. This is something that we don't have, and I agree that it can make it can have an effect that we cannot control for, and this leads to my second point, that it would be great to have richer data sets. I think this is an important point for the whole community of science, centrometry. So we should we need to make our data sets as rich as possible in terms of information to add more causal explanations. So if we could have more information about the living conditions of the scientists, for example, we could understand more. We don't, to my knowledge, we don't have such fine-grained and rich data sets as of now. But we can at least do something with what we have at hand, and I think we should study the information that we have. But I do agree that where you live has definitely an effect on many things, on job placement, or even on things like academic output.
Sorry, if it was my
sorry. Yes, sorry. There are many other questions, so if you can please maybe write your question to the chat, that would be great.
No, it is only about the comment that she just said. You said that your slides that 2% is matched based on the affiliation, means that where they work is important, yeah?
Yes.
Yeah. Thank you for that.
So yes.
Thank you. Yes. So I believe the question was asked by Benjun first. Sorry, Han. So also, if you can please turn on your camera so we see real faces, that would be ideal. Thank you.
Okay. Yeah, I just turned on about the way to calculate the demographic parity you mentioned in your talk. So I still didn't get how to calculate that indicator. So can you clarify how to?
Yes. So it's done this way. Say you have a ranking. You have 100 scientists, okay, ranked. The scientists are men and women, okay? And then you look at, for example, at the top 1%, the top 1% is not good. Top 10% of the ranking. Top 10% of the ranking is 10 positions in a ranking of 100 people. So for these 10 positions, we look at how many women and men we have. So say that we have 8 men and we have 2 women. Then here the balance is 80% men and 20% women. If we have 50% women and 50% men in the ranking in 100 people, then the parity would be 50% 50%. So the unfairness is usually measured as the difference between the parity 50% and 80% in this case. So 30 is the difference. Does it make sense? Hello? There is.
Hello,
am I frozen?
Yeah. I think yeah.
Okay, so it dropped. So, but then the demographic parity is a function of the portion of the ranking that I look. So if I look at 100% of the ranking, I need to have demographic parity because I look at the whole population. So at 100%, I see 50% men and 50% women. Yeah.
Okay. Thank you for your answers.
Thank you. Sure. Yeah, I went a bit fast on this. I know.
Han, go ahead.
Okay. Thank you, Roberta, for your interesting talk. I do have one question. Like for your Q model, and you can predict the career. I'm wondering, is that possible, or is it okay for the school to use it to hire for hiring or tenure case, or can I use for myself? Like I put my data in and I will see like how will I look like? Do you think that's possible? How can I guide myself with this kind of research?
So you're asking about the interpretation of how should we interpret Q, or how should we use Q?
Yeah, how should we use R?
Okay, so I say what you shouldn't do, and then I because this all depends on the interpretation that we give. So I definitely say that we shouldn't rank scientists based on Q and, for example, give funding on saying that based on Q, this scientist is better than another one. And the reason is that Q, so when we made the Q model, what we wanted to have is a model that can capture the statistical properties of a career. We never proved that Q is better at identifying good scientists than any other parameter, right? This is research that as of now is lacking, right? So I wouldn't claim that we need to use Q to rank scientists, because this has not been validated, but we can use Q to summarize the statistical properties of a scientific career. So, for example, if my task is to predict the number of citations in 10 years down the line of a scientist, then we can use Q. Q is a good predictor for doing that. But then we have to agree to rank scientists. We need to agree that just number of citations is a good way of evaluating or ranking scientists. Does it make sense? this difference?
I see. Thank you.
Yeah. And if you look at the paper, I know that you find a part where, for example, we predicted based on Q the cumulative number of citations or the age index or something like this. The reason for that is that, well, first it was asked by the editors and the referees, so it's a lot of the backstage that we have in papers. They wanted to see that Q has predicting power. And basically this, so that we were claiming it's a good model, but I think many people read it as it's a better indicator of quality, which is not necessarily so, especially after 6 years of more research into this realm. So if I could add an appendix to that paper, a small paragraph explaining this, I would do it. I can't, but I do it in talks usually.
Thank you, Roberta. So let's finish with Humin. Last question.
Hello, thanks for presentation. I have a question about the fairness. And you want to correct like the citation bias. I feel like the citation is not an issue of only about the paper quality, and maybe for males they are more likely to be social and promote their papers offline, and I feel like the citation might be caused by this kind of all kinds of confounding variables, and I think I'm wondering if this is meaningful to pursue the absolute fairness, or I think it's just a kind of natural social mechanism. Yeah.
Yeah. So it could be one of the factors, right? So if we could control for proxies of this, right? Online presence and self-promotion and so on, I think we could understand better the causality of this. So we don't know why a ranking is more unfair or fairer, right? I know that there is excellent work in promising directions in the field of alternative metrics, or people that try to combine different data sets, some on social media presence and publications. And I think these are all promising directions that we can take. So yes, so I think that the answer is that yes, this can be a confounding factor, and there is potential in taking some of the information from these factors and put it into algorithms to make them even fairer and more unbiased. And it's a collection of effects, right? We need to find all of them or as many of them as possible to create something that is as fair as possible, right? And there is a lot of work to do in this direction, and understand if it's doable. Sometimes it's doable, feasible, sometimes it's not, but at least I think we should be aware whether it's possible. So yeah, so a bit of a vague question, but we can vague answer, but I think we can explore this in one of the mentor session, perhaps.
Excellent, excellent invitation for the mentorship section. Thank you so much, Roberta. Let's thank Roberta for her talk. Virtual applauses. So looking forward to hearing more about this research. Very interesting.